Alright, today we're going to talk about probability of compound events. So whenever you have a compound event, okay, that means you have multiple events happening, say two or more. You have two different types. You have mutually exclusive and then not mutually exclusive. So when you have a mutually exclusive event, basically what that means is it cannot occur at the same, two events can't occur at the same time. Like you can't have an even and an odd number. You can't have a sophomore, a junior, and a senior all be the same person. One person can't be a Democrat, one person can't be like a Democrat, Republican, and independent. Whenever it's not mutually exclusive, then that means two things can happen at the same time. So you can have a male that's a Republican, a senior student that's a female, a Republican male that's under 40, things like that. So whenever we use a Venn diagram to kind of see how everything relates. So whenever we have mutually exclusive events, it's like one or the other. Okay, there's no overlap here. Okay, whereas everything that we're talking about, it's like you have a group in A and then you have a group in B. Okay, you can't be both. So whenever you have not mutually exclusive events, basically what that means is there's going to be some overlap. Okay, like if we have a male and female group, or if we have males and then we have people that are juniors in high school, there's going to be overlap there. Okay, there's going to be male students that are juniors. So whenever we talk about mutually exclusive, I need to go back to that. We're going to take the probability of whatever event A is and then add it to whatever the probability of event B is. Whenever we talk about not mutually exclusive, then there's going to be a little bit added to it. Okay, you're going to take the same two probabilities, the probability of part A, you're going to take the probability of part B happening, and then you're going to subtract where the overlap lies. Okay, in that kind of that middle section, where everything overlaps right here. Okay, where everything overlaps there, that's what we're going to take away. So you're going to actually have to do what's called a compound probability or compound event. That's what that AND event is. So that's the intersection. Okay, it's never empty. So that means even if it's one person that applies to both situations, there's still going to be somebody in it. If there's nobody in it, then they're completely dependent or independent of each other. So is what we're going to say mutually exclusive, or is it a compound event? So if I roll a single die, okay, then is it going to be mutually exclusive or compound if can I get an even number and a number less than 3 at the same time? So 6 sides, number that's smaller than 3, and even, the only one that can happen is going to be a 2. So it's going to be a compound because two things can happen. I can have a number that's less than 3, and I can have a number that's even as well with the number 2. Can I get an even and an odd number at the same time? We've already talked about that. That'd be a big no. Can I get a 2 and an even number? Okay. Yes, because 2 is an even number. That fits to where it's a compound. Okay, that's the only time it can happen, but there's still at least that one time. And then, can I get an odd number and a number less than 3? Okay. It doesn't say that I can get 3, but still I can get the number 1, which is less than 3, and is also odd. And then can I get a number that is greater than 3 and a number that is greater than 4? Okay, this cannot happen because there's no such thing as a 3.5 on a die. Okay? And because 3 or 4 is not included, it can't happen. There's no overlap there. So it's mutually exclusive. It's not going to happen. Whenever we use addition rules for probability, okay, that's the probability of 2 or more events that can be calculated. So if events are mutually exclusive, then it's an A or a B, and we're going to add the two probabilities together. Again, if it's a compound event, then we're going to take the same part, the probability of A plus the probability of B, and then subtract that overlap, okay, of whatever we have. So a card is randomly selected from a standard deck of 52 cards. Probability that it is an ace or a face card. Okay, key word there is or. Okay, one or the other. So in this case, it's an or statement. Okay, an ace or a face card. Ace is not a face card, so it doesn't apply to both things. Okay, if it talked about like a king or a face card, then that would be a little bit different. But since ace is not a face card, it's going to be two separate cases. So there are 4 aces. There are 12 face cards. So I will take 4 over 52 plus 12 over 52 and then add those together. One thing that I would suggest whenever you do this is don't simplify. Like, you could simplify 4 and 52, you could simplify 12 and 52. I wouldn't simplify anything until I get finished, because I have common denominators. Whenever I add the two fractions together, then I get 16 over 52, then I can reduce. Whenever I talk about mutually exclusive events, so I have a container or a bag of M&Ms. There are 5 reds, there are 8 brown, 3 yellow, and a blue. Find the probability of selecting a yellow or a brown. So, chance of a yellow or a brown, 3 out of 17 plus 8 out of 17. So, again, 11 out of 17. And then, again, you can put the percentage, but remember, make sure you put the approximate as far as that is concerned. It says a door prize here is given to a student at next week's assembly if you have 325 seniors, 382 juniors, 402 sophomores, and then 395 freshmen in attendance. What's the probability that a junior or senior will win? Since there can't be any overlap with this, then just take the total number of people, probability of the juniors, probability of the seniors, add those together. 1,504 people, 382 divided by 1,504 plus 325 over 1,504. Add everything together. 707 out of 1,504 people. Then, card randomly selected from a standard deck of 52 cards. Probability of heart or a face card. Now, this is a different scenario, okay? Because I have hearts that are also face cards. So there are 3 cards, the Jack of Hearts, the King of Hearts, and the Queen of Hearts, that aren't included. So that's where it's going to be my other formula, because I have 3 in the overlap area, or in that compound event. So whenever we do this, I'll take the probability of A, which is probability of a heart, 13 out of 52. Probability of a face card, there are 12 of those, but there are 3 that are hearts and face cards, so I have to take the 3 that I've already figured in the hearts or the face cards that I can only count it in one area. I can't count it in both. Okay, so that's why we take the 3 out of 52, because I can't count things as happening in both groups. It can only be associated with one group. So 13, 12, and 3, 22, divided by 52 or reduced, 11 over 26, about 42.3% or 0.423. Whenever we talk about compound events, so peanut butter or peanut M&Ms have been added to the candy dish from the previous example. Contains 5 red, 8 brown, 3 yellow, 1 blue still, but now it has 2 red peanut M&Ms, 7 brown peanut M&Ms, 6 yellow peanut M&Ms, and 4 blue peanut M&Ms. What's the probability of getting 1 yellow? What's the chance of getting 1 yellow or a peanut M&M? So you've got to basically think that you're going to not be able to see into the bag or whatever you're grabbing, or the dish or whatever. You're just blindly picking one out of the pile or out of the bag, however you want to look at it. So in this case, you have yellow M&Ms, okay, or one that's yellow, okay. So that's all the yellows, peanut ones included, all the peanut M&Ms that are included, but then you've got to take away the 6 yellow peanut M&Ms that you have. So 3 plus the 6 gives you the 9. 2, 7, 6, and 4 are all the peanut M&Ms that we have, but then we took away the 6 yellow peanut M&Ms, and we end up with 22 over 36, which is about 11 out of 18. Okay, so pretty good chance that you would either grab a peanut M&M or just a yellow M&M in general. So here it says 325 seniors in the earlier problem, 165 are female, 31 of the seniors are in marching band, 20 of those are female. 18 of the males play on the football team. So whenever we make a table showing the sample space or what we're dealing with, so we have 31 band members. We already know that 20 are male, or female, 11 are male. We have 18 male football players. We have none that are female. So as far as what that leaves, as far as being just a female, just a male, would be of what's left of the 165 or the 160, have 145 that are left, 131 male students that are left that aren't in marching band or football. Okay, 276 total people, okay, that aren't in either of the two. So the probability a senior is male or in band. Well, male, band, but then you have to take out the male marching band members. So 160 are males, 31 are in marching band, but 11 of them are males in marching band. So you have to take those away. So 180, about 36 out of 65 people. Then, probability of not something is called a complement. Okay, it's going to look very similar, or we're going to take 1 minus whatever the probability is. It'll also have like the little apostrophe, okay, with it. So like a card is randomly selected from a standard deck, find the probability that the card is not a king. Well, there are 4 kings, so it's everything that's left. So not a king is just going to be 1 minus 4 out of 52, or 48 out of 52, which is going to reduce to 12 out of 13, which is about 92.3%.